Hello everyone. In the previous sessions, we talked about propositional logic, and today we are going to continue with proofs. And in the next weeks, hopefully, we will see the application of these topics as well. So let's go through these terminologies first in theorems, and we will see about different types of proofs as well. Let me activate the laser. Yes. So formally, a theorem is a statement that can be shown to be true. So in this format, it's very close to proposition, right? Let's continue. In mathematical writing, the term theorem is usually reserved for a statement that is considered at least somewhat important. So it's not like all the propositions that we already shown can be called as theorem as well. Theorems should be important. In which way? We will see, for example, in some mathematical problems, such theorems can be very useful in order to solve them. And that's why they became known or famous. So those propositions which are not as important as theorems, so we just call them propositions as they are. And sometimes we call theorems facts or results as well. It is true, but sometimes they can differ, and I will explain it exactly in the same page. Because, yeah, theorems generally, they are so solid that we call them even facts, that nobody can disprove them, for example. But let's continue, and I will show you the difference between them. So a theorem may be universal quantification of a conditional statement with one or more premises and a conclusion. We talked about it, and we showed you the definition of argument, and this is related to that. So, however, it may be some other type of logical statement, as the examples later in this chapter. When we say in this chapter, we mean chapter 1, and also in the next slides, I will show you what we are talking about here when we say about this chapter. And we demonstrate that a theorem is true with a proof. So instead of argument that we said, for example, this argument is valid or not, for theorems, we say we have a proof for that or not. So a proof is a valid argument that establishes the truth of a theorem. So you see, these definitions are pretty close, and time to time they are exactly the same. But now we know, for example, when we talk about theorems, right after it, we talk about proof, which is the valid argument which establishes that. So the statements used in a proof can include axioms, which are statements we assume to be true. That exactly shows the difference between facts and theorems, because we have some assumptions in theorems that we have. For these assumptions, we say that this is true, so we can prove our theorem. But for the fact, this is not the case that for any situation it should work. And that's why we should know about this important difference. But in mathematics, most of the problems that mathematicians already found the proof, those assumptions are totally valid, and we can't even call them facts, and nobody can disprove them anyway. So the next terminology which is important is lemma. So a less important theorem that is helpful in the proof of other results is called a lemma. So lemma is also a proposition, like exactly theorem. But the difference is that we need these lemmas in order to prove our theorem. So instead of having a huge theorem with a long proof, so it's not a bad idea to deal with the partitions of that theorem separately and call them lemma. Then for our theorem, we can just use those proofs and then prove our own theorem. And the next terms which we hear a lot, corollary and conjecture. So corollary is a theorem that can be established directly from a theorem that has been proved. So right after it, there are some results that which is different from the conclusion of the theorem, but there are some results, which is the subsequence of what happens after it anyway. And a conjecture is a statement that is being proposed to be true statement, usually on the basis of some partial evidence, heuristic argument, or the intuition of an expert. So this conjecture is very close to axioms, as we mentioned, which are pretty much like assumptions that we use in our theorems. Now, the part related to types of proofs, because we can prove our theorems with different approaches. Like for the direct one, we try to prove that Q is true by showing that starting from P, because P can be our initial point, and finally we reach that Q is true as well. So it's not as simple as this, but it shows us the direction. It means that first I show P implies R, then R implies S, and S implies Q. So there are series of propositions, and we show them how we can illustrate them using arguments or argument forms, and then have our conclusion. So direct proof is very common, and we see a lot in mathematics. Proof by contraproposition. We already showed that this compound proposition is equivalent to this one, right? So now you can see why they are useful. That these terms that we showed that these two, for example, are equivalent. Now it's useful because we can use it as an approach of proof. So if you show such a case is true, it means that you prove that this term is true, because sometimes it's not easy to prove my propositions, prove my theorem by using the direct proof like that. So this one can be helpful. And also we have another one, contradiction. And for that, we use this compound proposition, and we will show that the negation of P is false, and we reach contradiction. And showing that this one should be false, then P itself is true, and it concludes that Q is true at the end. There are several examples related to them in the book. I'm not going to go through the details, because at the end I won't expect you guys to come up with your own proof for other theorems. So that's why I want you guys to be patient, because starting from next week we will see lots of examples, including chapter 1. So the other types of proofs. Proofs of equivalence. So this one is based on tautology. What was that? Tautology, we also remind you last session that the last column of the table of truth for both sides should be always true, right? So we will reach tautology. And in that case, we could show that two compound propositions were equivalent. And another method is counterexample. Counterexamples can be very useful because, for example, in the theorem, it says for all values of x, we want to show that this is true. And you will show, for example, with just one example, that for this x, it doesn't work. So this compound proposition is false. So this is very good approach in order to just cancel the whole theorem. But if you want to prove it, then in that sense, you can use counterexamples to, for example, prove that the negation cannot be true. So the proposition itself is true. So this is a good method also to use for proving our theorems. And exhaustive proof. In this case, we try to partition our propositions into different partitions. So instead of saying that P implies Q, I can partition them into P1, P2 to limited number of them, for example, n number of them. And then if I want to do that, I should use this tautology. It means that one by one for each partition, I should show that this is true. And if it is true for all of them, it means that this proposition is true, and this one will lead to Q. But this one also we can consider as proof by cases, like we have such a condition that instead of P, we have PIs. So some partitions inside P. Another famous one as a method of proof is without loss of generality. And we can also show the abbreviation of that, WLOG. And for this one, especially, it's very useful for sequences or series in mathematics. We just check for some terms whether it is true. And also, we can show that the next term of sequence, can it be generated from the previous one, and does it hold for the whole limited number of sequences or not? Instead of checking for infinity number of them, just by showing the trend, we can prove things by using without loss of generality method. And we have another one named existence proof. So let's read this one. Many theorems are assertions that objects of a particular type exist. A theorem of this type is a proposition of the form there exists one x of this function, where P is a predicate, and a proof of a proposition of the form there exists x Px is called an existence proof. So in that scenario, we are looking just for existence of one element inside that function. And this is very easy to find. So this kind of proofs are pretty easy if we can use them. And we call that a specific number or value witness. So witness corresponds to that. If you can find the witness, then in that case, we can prove that this is true. For example, can we say there exists one value for x, which x plus 2 is equal to 0? Yes, for example, -2 is our witness here, because it is possible to find that, and I showed it that -2, which is here called A, is our witness. So another one is called uniqueness proof. And for asking questions about, for example, theorems which are related to uniqueness, we should follow these two steps. First of all, we should say that such an element exists. So by using the previous method, the existence proof, we show that. And for the next one, for the uniqueness part, we should consider an arbitrary variable, and we should show that it's not possible that y wouldn't be equal to x. It means that any elements that you will find inside that function should be equal to x. There is no other way. So at the end, we should reach this term x equal to y. So this one is very useful in order to find uniqueness of some variables or values, and you can also see lots of examples related to them. So, so far we introduced you logic and proofs, and we covered chapter 1. We haven't seen that much example in the lectures, and there's a reason for that, as I explained, because we want to see the application of that. We don't want to ask questions related to pure mathematics from you. So at the beginning, maybe it's a little confusing because you don't know which part of the book is more useful for you. But anyway, my suggestion to you is to go through all examples in the book anyway, as much as time allows you. And from the next week, you will see your weekly assignments and the questions that you get more familiar with the course, and you know which part of the book which is interesting for engineers and computer scientists in general, and we will for sure focus on that more. And next week we will also start talking about sets and functions, and things will be maybe easier for you because we are getting a little far from pure mathematics, but still we need those terms anyway, because you will see that for learning about sets and functions, we need to know about logics and, for example, compound propositions, something like that. Otherwise, we just memorize things without understanding them. So that's why the first chapter was useful, to have better understanding of the next topics that we will talk about. So if you have any questions, please ask me. Otherwise, especially from the next week, in the second part of our Fridays, usually deal with questions and examples that we had for the sessions. Okay, guys, so if you have any questions, please let me know.